Chapter 1, Bond Formation and Lewis dot structures. With Lewis dot, Lewis understood that the atoms transfer or share electrons in such a way as to attain a filled shell of electrons. In other words, the s orbital will always have total of 2 electrons when it's full. The p orbital will always have 6 electrons, and when you put them together, you will get 8 electrons. And what that does is allow these atoms to become isoelectric, which means they have the same electronic configuration as helium, neon, or argon. So hydrogen is going to have 2 electrons, so it is technically then 1s2. But it's going to have a negative charge in this case, etc., because it gained an electron. There's either transfer or it shares that electron, allows that to happen. So what they're trying to do, except for hydrogen, is fulfill the octet rule. Hydrogen is an exception. The filled shell has 8 valence electrons, 2 from the s and 6 from the p, for a total of 8. And this will always hold true for the second row of the periodic table. Always, always, always. So hydrogen and helium doesn't have the 8, but the second row does. There are some exceptions to that, which we'll get to here. Elements in the third row or higher can have what is known as the expanded octet rule, which means there's the D block working for them. So sulfur, we could have sulfur tetrafluoride. And we'll eventually get into molecular structures. So here is sulfur hexafluoride. So sulfur had a total of, supposed to be electrons there, 2, 4, 6, 8, 10 electrons now around it instead of 8. We can also have sulfur hexafluoride. In this case, it's going to have 12 electrons. That is the expanded octet rule. There are times when aluminum may have 3, but it can, because of this D block, accept a pair of electrons. In other words, there's bonds here. So that's still expanded. And this happens in organic chemistry quite a bit with aluminum, especially later on in the semester. So with bonding, 2 types of bonds, and we have these in organic chemistry also, and they're extremely easy to see when it happens. We can have ionic bonds where there is a transfer of electrons. So lithium has 1 electron. Chloride has 7 based upon its placement on the periodic table. So the electron from the lithium goes to the chloride. And now we have lithium. See if I can write that a little bit straighter. With a plus charge. And chloride now has 8 electrons around it. And it has now a negative charge. And then normally we would write them lithium with a plus charge and chloride with a minus charge. for our ionic bond. And we remember ionic bond is usually a metal bonded to a nonmetal. And that will hold fairly true in organic chemistry also. And these normally form nice crystal lattices. Covalent bonds is where they share of electrons. So we have a hydrogen atom and a hydrogen atom form an H2. So S overlaps with a S, and the two overlap here. And this overlap is where they share the electrons. And this is an example of a covalent bond. And most covalent bonds are nonmetal with nonmetal. And carbon is nonmetal and hydrogen. So we're going to try to draw Lewis dot structures for this. So with Lewis dot structures, we're interested in the valence electrons only. So we have methane, which is CH4. It has 4 valence electrons. So according to the Hund's rule, we have to singly occupy each space. So I just put 4 dots around it. And for a hydrogen, it has 1. And the electrons can move, but this one was made simple intentional. So we have put 4 hydrogen on here, and it's pretty obvious where we're going to stick the hydrogen. We have 4 single electrons. And there we have it. Sometimes we just draw it. Each line represents 2 electrons. And this is the Lewis dot structure for methane. And there are 8 electrons around this carbon for the octet rule. So we have 2, 4, 6, 8. It's going to be important because some of you will try to draw 10, some of you will try to draw 6, or any number in between there. Been there, done that. So let's look at methanol. It is an alcohol. So our carbon's going to have 4 valence electrons around it. Our hydrogen's going to have 1. Now oxygen has 6. 1, 2, 3, 4. I put 4 around it. Now we can go back and pair them up. So oxygen looks like it has 2 bonding sites. So now we have to try to build this molecule. And I'm trying to give it away. There's going to be 3 hydrogen. Now I can't put another hydrogen on there because then there's no more free electrons. So I need to put the oxygen. So I'll put it in blue. Now if we look at this carbon right now has 8 electrons around it. We still have 1 more hydrogen to go, so we can put it right here. So what we have is and I'm going to straighten it out. It's not linear, but I'm going to draw it like this, and this is methanol. It has a pair of non-valence bonding electrons. Sometimes we just call these a lone pair. And you want to make a habit of always showing the lone pair. Because if you remember right, electrons always, eventually you're going to figure out that reactions always occur around electrons. So those lone pairs are important. In fact, this would be called electron rich. So if I have chloroethane, I'm going to put my two carbons together, and we know carbon always has to have 4 bonds. So now that carbon has 4. This carbon now has 3, so it's going to bond with a chloride. And this chloride is going to have 3 sets of lone electrons. So these are our lone pair. So there are compounds that have multiple bonds. So we can have a double bond or a triple bond. In a double bond there's 4 sets of electrons. In a triple bond there's 6 sets of electrons. So an example of a double bond, we're just going to go CH2O. We have carbon. Well, I'm just going to put my hydrogen here. And then there's going to be 2 bonds for my formaldehyde. So I have a C double bond O with an H and an H coming off the carbons with 2 lone pair. Eventually we're going to learn that oxygen is very slightly electronegative, so it's going to have a slight negative charge, and that means this carbon is going to have a slight positive charge and be called polar. That's for another video. Just to remember that. Whoops. If we have triple bond, this is acetylene. It has a triple bond, but if you notice the carbons in both of these cases still have a total of 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. That's 2, 4, 6, 8. And this one also has 8, so it will always follow the octet rule. Here's a general rule to help when you're drawing Lewis dot structures. And it's for patterns. And these are for uncharged molecules, because when they become charged, like a hydronium ion eventually, the rules will change. So carbon will always have 4 valence electrons. Nitrogen, which means it's going to always have 8 total electrons. Nitrogen will always have an electron pair, 1 electron pair. It has 3 bonding electrons and 1 electron pair. Oxygen will always have 2 electron pairs and 2 bonds. Hydrogen will always have just 1 bond. The halides, like chlorine, bromine, fluorine, and iodine, they will always have 1 bond and 6 pairs of electrons. Sulfur will always have 2 electron pairs and 2 bonds. Well, I wonder why. Because they're in the same family on the periodic table. Why are the halides the same? Because they're in the same family on the periodic table. So that will always hold true for uncharged species. We will do more Lewis dot structures.